Chapter 2, we're going to talk about alkanes and cycloalkanes. Now, when we just mentioned those functional groups, the alkanes functional group is just carbon single bonds, and so that's what we're going to see here. Just some general terms that are helpful to know. If you see words in bold on a PowerPoint slide, you should have a working knowledge of what those words mean. I'm not going to ask you to, produce awesome definitions or anything, but I'm going to assume that if I use the word hydrocarbon on an exam question, that you're going to be able to know what that means. Okay, so when we talk about hydrocarbons, these are compounds that only have carbon and hydrogen, nothing else. When we talk about a saturated hydrocarbon, that means we've only got single bonds, no double or triple bonds. Unsaturated hydrocarbons contain at least one carbon-carbon or double or triple bond. They could have more, they could have a lot of them, but at least one. If there's even one double bond or one triple bond, it's unsaturated. And as a subgroup of those, we have the aromatic hydrocarbons. And we'll talk more about these later, but these are related to benzene. They are unsaturated in a very special way. So, for these saturated hydrocarbons, they've got hydrogen and carbon and single bonds only. We call them alkanes if they are acyclic and cycloalkanes if they're cyclic. So alkanes have single bonds. Cycloalkanes also have single bonds, but they form rings. So the simplest alkane is methane, CH4. And we've looked at that a lot, and its shape and everything. Well, larger alkanes are just going to have longer carbon chains, and they're going to have additional hydrogens to complete the carbon valences. Carbon wants 4 bonds. They're all going to be single bonds in the alkanes. And so I wrote a note to myself, draw some alkanes. So we could have an alkane that has 3 carbons instead of 1. The carbon's attached in a line there. And then it would need to have hydrogens to fill the remaining bonds for the carbons, because the carbon wants to have 4 bonds. We could have, sometimes they are not in a straight chain, they can be branched, but we look first at the carbons being attached to each other with single bonds, and then we have to fill in so they all have 4 bonds. And that's where drawing things in this expanded structure form with right angles is nice, because we need a bond on the top and the bottom and the right and the left. And so it's very geometric, and we can predict, oh yeah, we need a hydrogen here and here and here. And as I mentioned before, drawing all these hydrogens is tedious after a while. But those are examples of alkanes. Here are more examples of alkanes. This is a useful table. So the number of carbons in the chain and the name and the molecular formula. This is a somewhat abbreviated structural formula. So decane has 10 carbons, and instead of writing out all those CH2s, it's CH3, and then there are 8 CH2s in a row, and then another CH3 at the end. We're always going to end up with a CH3 at the ends, because the carbon is only bonded to one other carbon, and so it's got 3 hydrogens. The ones in the middle are CH2. And these all follow this general molecular formula of CnH2n plus 2, where n is the number of carbons. So if we have n equals 8 carbon atoms, we can predict the number of hydrogens that the alkane will have, because if n is 8, 2 times 8 is 16, plus 2 is going to be 18. And we see that octane is C8H18. So this is a useful little guide to remember. These names we will come back to, but I want you to notice after you get past the first four, pentane, hexane, heptane, octane, nonane, decane, do the prefixes of those sound familiar? They are like the prefixes we used to name binary molecular compounds in general chemistry. The first four are just weird. I'm not exactly sure where they came from. We just have to deal with them. We'll get back to naming, but normal alkanes, or sometimes called N-alkanes, N for normal, these contain unbranched carbon chains. And the only thing that's different from one normal alkane to another is the number of methylene groups. That's the CH2s. So, we can have something with 2 CH2s in the middle. How many total carbons are in that compound? 4. Or we could have, there's always a CH3 on the end, CH2 in the middle. We could have 5 CH2s in the middle and a CH3 on the end. These are both normal alkanes. They're just straight carbon chains, nothing fancy. We sometimes use the term homologous, a homologous series. So the compounds in a homologous series are built up in a regular repeating way. And if we look at that, I'll go back to that table in a minute. Well, let's just go there now. If we look at this table, this is a homologous series. Because what we're doing here is we're adding a carbon and we're adding 2 hydrogens. And it just increases as we go down. It's being added to in a normal, regular repeating way. And members of such a homologous series tend to have similar physical and chemical properties. There are millions and millions of organic compounds. And so nobody can possibly know the properties of all of them. But by understanding the properties of the different groups, we can have a clue about what's going on with the individual members. That's my husband making faces at me.